Good morning. So we have a connected particle subject extension today, and as you can see from the question, it's quite an interesting question because it's very different to a lot of the connected particles questions that you have seen before, which primarily focus on inclined planes with a particle dangling off the end, or a bench with a particle dangling off the end, or even two particles connected on a horizontal plane. This one, as you can see, we have two diagonal planes with the pulley at the point C at the very top, and we're going to have to do a little bit of extra resolving, but the point of working through this question is just to really show you that the process is no different to that you're used to. So to kind of read through the blurb, we've got this diagram here that shows a particle X of mass 3 kilograms on a smooth plane, which is inclined at an angle 30 degrees to the horizontal. Now, that should be familiar territory when we've been resolving inclined planes up to this point. Now, we've also got a particle of Y of mass 2 kilograms that's also on this inclined plane. And this inclined plane, B to C, is at an inclination of 60 degrees to the horizontal. The two particles are connected by a light inextensible string, and the length of the string is 2.5 meters, and it's passing over a smooth pulley at C, which is the highest point of the two planes. A lot of information. Initially, Y is at a point just below C, touching the pulley with the string taut. Now, this is really important. We'll come back to this later in the question. The diagram makes it look like particle Y is at some distance from the pulley, when in fact we read the blurb and we can see that it is touching the pulley. The particles then are released from rest. They travel along the lines of greater slope, AC in the case of X and BC in the case of Y. A and B are the points where the planes meet the horizontal ground. AB is 4 meters. There's a lot of information there. The question then goes on to ask us three things. Show that the initial acceleration is given by this. Interesting that it's written in terms of G. We're not actually asked to write this as a decimal value, worth 7 marks. By finding the tension, or otherwise, find the magnitude of the force exerted on the pulley. That's always an interesting question, when the force exerted on the pulley. And find, correct at 2 decimal places, the speed with which Y hits the ground. So, the very first thing we need to do before we go any further is to label our diagram with all of the forces. And that's really important because this is the part of your working that does all of the heavy lifting. If you have a good force diagram, an accurate force diagram, then there is nothing that they can ask you in this question that should make you stumble. So first of all, let's put our weight to each particle. So we've got X, which has a weight pointing vertically down, and we have Y, which also has a weight pointing vertically down. So there are my two weights. The weight of X, well, it has a mass of 3 kilograms, so its weight is 3g newtons. The weight of Y is the mass 2 kilograms multiplied by g, so 2g newtons. Now those weights need to be resolved parallel and perpendicular to the plane. Now this is something that you are already familiar with. So we've got our perpendicular to the plane for this particle X, and we've also got a force parallel to the plane for this particle X. And when we actually want to work out the size of the component, then this perpendicular force is given by 3g multiplied by cos of the angle. Okay, so 3g cos 30. And again, standard. You've done this a lot when you've been resolving forces on inclined planes. This parallel force, therefore, is going to be 3g multiplied by sine 30. So this 3g has now been resolved into its perpendicular and its parallel components. We do the same thing for particle Y. So for particle Y, we have our perpendicular component, and we have our parallel component. And very much like particle X, this perpendicular component is given by, and I'll write it here and then move it, we've got 2g cos of the angle 60 And the parallel component, which actually, let's just put that in place first. So we've got 2g cos 60, that's our force perpendicular. And our parallel force is going to be 2g sine 60. Before I start writing cos again. Okay, so those are our masses, our weights, and we've resolved those weights according to the diagonal plane. The other force that we need to add in is going to be the tension in the string. Now the tension is equal on either side of the pulley because it's attached with a single string. So we have this equal tension joining X to Y, heading towards the pulley. Now we could add in normal reaction forces for X and Y, but our planes, our diagonal planes here, are both smooth. And the only time we need to use the normal reaction force would be when calculating friction. And so, because there's no friction, that's not something that's necessary for this question. One last thing that I will add in is which direction is my acceleration. So the acceleration, we've got an acceleration of y, and we've got an acceleration of x. It's the same acceleration. And the particles in this instance are moving, x is moving towards the pulley, and y is moving towards the floor. Now we get that information from looking at part C when it says y hits the floor, but also this steeper 60-degree angle is what's going to cause this y particle to move down as opposed to the x particle to move down. So there is our completely labeled diagram. Okay, we've got all of our forces that are going to be relevant to us. We've got everything pointing in the right direction, and we've resolved wherever things were not perpendicular or parallel to the plane. And only now can we start to get into the question. So we've been asked to show that the initial acceleration of the system is given by g over 10 times 2 root 3 minus 3 meters per second squared. So we're going to model each particle separately. We'll start with particle x, and we're going to use Newton's second law, F equals ma, where F is the resultant force, m is the mass, and a is the acceleration. So if we look down here at particle x, the way that it's going to move is up the plane. So that's our positive direction. So our resultant force is going to be the tension minus any forces that are acting parallel to the plane down. And the only force we've got acting parallel to the plane down is 3g sine 30. So t minus 3g sine 30 is equal to 3a. I'll simplify that a little. Sine 30, we know sine 30 is a half. A half multiplied by 3 is 3 over 2, so we end up with t minus 3g over 2 equals 3a. Now that's as far as I'm going to simplify that equation. I could substitute 9.8 in for g, but actually, look, our answer is left in terms of g. So that's going to be equation 1 of 2. The second equation is going to come from modeling particle y. So again, we're going to use F equals ma, and we're going to find the resultant force and use the mass, and then we're going to try to work out the acceleration. So for particle y is going to move down this slope, so the tension is moving in the negative direction. And so our resultant force is going to be given by the 2g sine 60 positive. Pardon my writing, it's very cold and I've forgotten how to write today. 2g sine 60 minus t, okay, 2g sine 60 is in the positive direction, minus the t, is going to be equal to 2a. Now, much as I did before, I'm going to simplify the trig. Our sine of 60 is root 3 over 2. multiplied by 2 just gives us root 3. So 2 times root 3 over 2 is just root 3. So we have g multiplied by root 3 minus t equals 2a. And that is our equation 2. Now this is all pretty standard stuff. This idea of modeling particles separately and then using simultaneous equations, that applies when the particles are both horizontal, whether they're both on an inclined plane, if one's on a table and the other's hanging off a table. It's always going to be this process, all right? And it's made easier by the fact that our diagram shows all of the forces in the right place and their directions. So all I've got to do now is add these two simultaneous equations together, because one has a positive value for t, the other has a negative. And adding the two equations will eliminate t from our equation altogether, thereby leaving us with a in terms of g. So we have minus 3g over 2 plus g root 3. G root 3 minus the 3g over 2 equals 3a plus 2a, which is 5a. And we're almost there. If we simplify this a little bit, then we can do, well, we can do a number of things. We could try, pardon that, we tried dividing everything by 5, I suppose, at this point, and we could say we've got 1/5 of g root 3 minus 3g over 10 equals a. That's looking good so far, because I know that I need g over 10 in my answer. And then we can just do, take whatever factor of g out that we can. And I'm just going to say, right, let's do g over 10, because that's what we're after. So g over 10, pardon me, what do we multiply g over 10 by to get 1/5 g? We multiply it by 2. And then we've got this minus 3, which is the value of a, as required. So you can see that the only difficult bit, I suppose, then, is simplifying this, perhaps. Okay, make sure your algebra is strong. But the rest of it should be very procedural. Write two equations, write them as simply as you can, add the two equations together, eliminating t, and then find what a is. If you're in a question where it asks you to work out the tension, obviously you then take a and you substitute back in to evaluate t, which is something we're going to need to do later in this question. So moving on. Part B says, by finding the tension in the string, or otherwise, find the magnitude of the force exerted on the pulley and the angle that this force makes with the vertical. So the first thing I'm going to do, actually, is I am going to find tension in the string. I'm going to use from part A the fact that our acceleration is g over 10 multiplied by 2 root 3 minus 3 meters per second squared. And I'm going to substitute that into a part of A. I'm going to use equation 1. Now, equation 1 said t minus 3g over 2 equals 3a. And if I go ahead and substitute, t minus 3g over 2 is 3. So 3g over 10, 3a I should say, 3g over 10 multiplied by 2 root 3 minus 3. So therefore t is going to be our 3g over 10 multiplied by 2 root 3 minus 3 plus 3g over 2. Now I'm just going to work out what t actually is. All right. It will come out as a decimal, but we'll leave that decimal in the calculator. So we'll do 3 times 9.8 divided by 10. And then we'll multiply by 2 root 3. Sorry, using the calculator as we speak. 2 root 3 minus 3. So we've got 3g over 10 multiplied by 2 root 3 minus 3. And then we're going to add 3g over 2. And our tension comes out as 16.06445 ... newtons. Okay. Now I'm going to leave that unrounded in my calculator because it is going to come back. That's what we're going to use. So now that we've got the tension, let's pay attention to this pulley. Now the pulley does experience a force, okay? We have to now consider the two tensions acting in the opposite direction than they were before, okay? They're both the same tension, but we've got two different forces here. Now, the reason that they're acting in a different direction is simply because we're asked about the force exerted on the pulley. And you can imagine that these two particles, when they're in the situation that they're in at the beginning, they are exerting this force on the pulley. They're trying to pull the pulley almost down towards Earth because we have these two masses that are trying to drag it down. Now, if you imagine, this is what I like to kind of say, but if you imagine holding your arms out in front of you, and someone grabs onto each arm and applies an equal force to each arm, where do you end up moving? You end up moving directly down the middle. And so what's happening here effectively, and this diagram is quite difficult to work with, so I'll work with this little triangle here, is we're actually going to take this angle here and we're going to end up cutting it in two. And our force is going to end up going right down the middle of this. Now, if we think about our diagram, what we're going to need to know is the angle here at C. If we've got a 30-degree angle here and a 60-degree angle here, it means that this whole angle here is 90 degrees. It's a right-angled triangle. All right? So this is a 90-degree angle. Where is this pulley? Where is the resultant force of these two particles trying to move this pulley? Well, it's halfway down the 90 degrees. Which means, in terms of my diagram, we have a 45-degree angle here and a 45-degree angle here. Okay? Because those two people pulling on your arms, you'd end up moving exactly down the middle, halfway between them, like an angle bisector. So to model this, let's have a look at actually showing this on a triangle. Okay, so I'll just draw a right angle triangle. I'll draw a couple of right angle triangles. We've got our tension that we're interested in. It's going to be here. Now, before I go any further, let's just put these together, duplicate, flip. We'll tilt it slightly to indicate this 45 degrees isn't vertically down. Okay, it's cutting the 90-degree angle in half. It's not therefore necessarily vertical. So let's do that. Let's do this. So here is a kind of visual representation of what's happening here. And I'll explain all of these parts in due course. So here is the tension. Here is the tension. Okay, this is the tension caused by X. This is the tension caused by Y. This angle is 45 degrees because we've split the 90-degree angle in two. And so therefore, this straight line down here is given by T cos 45, as is this straight line down here, T cos 45. So what we've actually got is a magnitude of T cos 45 produced by the tension in the particle Y. We have an equal T cos 45 produced by the tension in X. And so the resultant force that we're actually working at is given by two lots of T cos 45, one from X and one from Y. Now this is always the case if we're asked to find the force exerted on the pulley. We look at the point where the pulley is, we bisect the angle, and on one side of the angle we have a tension from one particle, on the other side of the angle we have a tension from another particle. And so we always end up with 2 times the tension multiplied by cos of whatever the angle is. So we can now go ahead and just directly substitute this in. We've got 2 times the tension, which is our 16.06445, dot, multiplied by cos 45. So we'll leave that 16.06445 in the calculator, we'll multiply it by 2, we'll make sure our calculator is in degrees, and we'll multiply by cos 45. And we get 22.7 newtons, and that's correct to 3 sig figs. So not bad for 7 marks. And again, it's fairly procedural. If you're ever asked to work out the tension exerted on the pulley, you're going to have to take double the tension, and you're going to multiply by cosine of the angle. And the angle that we're talking about is whatever the angle here is bisected. So, part C, find correct 2 decimal places the speed with which y hits the ground. So I've reproduced the diagram. I've copied the diagram here. I've put in our acceleration, and now none of our forces are really of interest to us, not for this question and not in this part of this question. But this is where this C is touching the pulley with the string taut. That's massively important, okay? Because if the particle y, particle y is touching the pulley with the string taut. If particle y is in the same place as the pulley, remember these are particles, okay? It's in the same place as the pulley. Then the distance that y has to travel is going to be the length of BC. Now that's not clear from the diagram. Okay, they've left the diagram like this so that you can see that there's a string here. But this is the sentence that you've got to pay attention to in the question. Y is at a point just below C, touching the pulley with the string taut. That's what's telling us that the distance the particle y travels is the whole of C down to B. So if we want to find that distance out, we can use SOHCAHTOA, because in this example, okay, so this is not a procedural part, this is particular to this question, but we can use SOHCAHTOA because we have a 90-degree angle. So using SOHCAHTOA, we can say that the cosine of 60 is given by BC divided by 4, because 4 is the hypotenuse of this triangle. BC is the unknown length, it's adjacent to the 60, so we can use that. So if we can calculate 4 cos 60, then we get our BC. Now cos 60, as you know, is a half, and so 2 is our length BC, 2 meters. So now we can use SUVAT, because we have a constant acceleration, and we're trying to work out speed. So the displacement is 2, that's the particle moving from this point down to this point. The initial velocity is 0 because the particles are released from rest. V is the thing we're trying to calculate, and the acceleration, we were told way back at the beginning, was g over 10 times 2 root 3 minus 3. So we use our equations of motion. We're going to use v squared equals u squared plus 2as, which means that v squared is 0 squared, u is 0, so 0 squared, plus 2as. So we've got 2 times s, which is 2 times 2, which is 4. So we've got 4a. So we end up with 4 times the acceleration, or 4g over 10, 2 root 3 minus 3. And we can just use a calculator to work out what that is and square root it at the same time. So we've got 4 times 9.8 divided by 10 multiplied by 2 root 3 minus 3. And then we're going to square root the answer. And our velocity comes out as 1.35 meters per second, correct to 3 sig figs. It asked for 2 decimal places, so we've got 2 decimal places. Now, that's the end of that question. And it looked difficult to begin with, but once we got into it, we found actually it wasn't too bad. Quite procedural. So I hope this video helped. I will post this video in the Teams chat in a few minutes, and I will also make available a PDF of the working for this, so you've got a document that has the working for this as well. All right, take care everybody. Bye-bye.